Okay, so the idea here is the following, that B1 is linearly proportional to I1. Furthermore, the only way we can have a time derivative of B1 is through a time derivative of I1. So it makes sense that we should indeed be able to write it in the following way. And furthermore, that if we compare this equation to this equation, straight away we find that M must be the integral of B1 dot dA2. So the magnetic field produced by this wire, by wire 1, dotted into an dot dA2 and integrated across this area. Okay, so this quantity here is called the mutual inductance, and often it's given a couple of subscripts, M1, 2, let's call it, meaning the mutual inductance of coils 1 and 2. Alright, so let's now study a simple example where we might use this, and the simplest example that we can consider is two solenoids, one inside the other. So here is a solenoid, here is solenoid 1, and we're going to put inside it another solenoid. This is embedded inside it. There it is. Alright, there's turns on both of them, so I'm sorry my drawing isn't that good, but I've got an inner solenoid inside an outer solenoid. They're different lengths. One has, let's say the outer solenoid has, let's say the outer solenoid has N1 turns per meter, and the inner solenoid has turns N2 turns per meter. And let's see, let's give them both the same radius. So in other words, the inner solenoid and the outer solenoids both have radius A. So in other words, if you like, the inner solenoid is jammed hard up against the wall of the outer solenoid, and we'd like to calculate the mutual inductance M. So to calculate this, we're going to calculate first of all the magnetic field due to the outer solenoid. So let's consider 1 amp flowing in the coils of the outer solenoid, the longer of the two, and that magnetic field is going to be the following. Okay, there it is. And what we would like to do is we'd like to integrate this magnetic field for a current of 1 amp across the area, or through the integral of B dot dA through this second solenoid. Okay, well that's fairly straightforward to do. Okay, so here is our result. Mu naught N1 is a magnetic field due to coil 1 for a current of 1 amp, and the area of the second coil is pi a squared multiplied by the total number of turns on the second coil, or the inner coil, which is N2, the number of turns per unit length for the inner coil, multiplied by L, which is this curly L, and this curly L is this length here. It's the length of that inner coil. So that's our curly L. Okay, so this then would be the mutual inductance for those two coils. So let's just write that down on on the next page here. For our solenoids, the mutual inductance would be the following. Okay, so there is that. Now, this has a great deal of utility, of course. This is the basis for a transformer. Let's say, for example, we were to set up two coils, one that looks like this, and there we go, and a second one that looks like that. And if a time varying current were flowing in this coil over here, it's going to produce a time varying magnetic field, and that time varying magnetic field is going to thread the second inductor over here, and the ddt of B dot dA is going to drive a current in this loop here. Okay, this is the idea behind a transformer. Now, in many times in practical situations, the way this is made is we might have a magnetic material. Here we go, I'm going to draw a square loop of magnetic material, might have magnetic susceptibility chi, and the coils are actually wrapped around this thing. There's our primary windings, here's our secondary windings, and this magnetic material really helps guide the magnetic field if we were to do the calculations, so that we get maximal coupling of the magnetic field between the two coils. And this is a very common design for a transformer. Now, for those of you who use some sort of petrol-driven transport to come to work today, let's say a petrol engine, not a diesel engine, you would have used this principle as soon as you turned on your car, and you might have asked yourself the question, how is it that if I have a car that only has a 12-volt DC battery, that I can get a spark across a spark plug, which is thousands of volts for that spark, to ignite the petrol in my cylinder? Well, the way that works is the following. Okay, so what we have is here's your car battery, here is the primary side of your ignition coil, and you have a switch that can be open and closed. Okay, you then have this primary coil coupled to a secondary coil, and these are usually wrapped around each other to maximize that coupling. I can't draw that picture, so I've drawn it like this, but the point is the magnetic field from this coil threads this coil. Okay, if you look at the previous, if you consider this situation, you will get a all right, so in a situation drawn now, on opening or closing this switch, we drive a time varying current through this coil. If we have a large number of turns on this secondary coil compared to this primary coil, we get a step up in the voltage, and you can calculate that from the equations that I've shown previously. This changes 12 volts into kilovolts, or many kilovolts, and those many kilovolts produce a spark that I've drawn here across your spark plug. And if you now embed that spark plug in a piston, there we go, let's try and draw that. There's our car cylinder, and here's our piston. And if we put petrol then in this region here, then this spark ignites the petrol, pushes this piston down, and we use that energy to drive the wheels of the car. Okay, so there is the basics of an ignition circuit in your car, and it's the way you turn 12 volts DC into many kilovolts to ignite the petrol to drive you along and make a contribution to the destruction of the atmosphere of the planet. Happy days. I love my car. Actually, I love my bike more. Actually, I love my dogs more than my bike. Yeah, anyway.